Bismillahirrahmanirrahim. Assalamualaikum. So today we are going to discuss the course Inorganic Material Chemistry. Course code is CAM 3115, and we will discuss topic is properties of advanced materials. And under this topic, properties of advanced materials, today we will discuss dielectric properties. In today's lecture, we will discuss about advanced materials and nanoparticles, their introduction, and then we will, as our main topic is dielectric properties of advanced materials, so we will discuss about dielectric nanoparticles and why we can use dielectric nanoparticles and what is their importance. And then types of dielectric materials, that is about paraelectricity. There are two types. One is paraelectricity, and other type of dielectrics is ferroelectricity. And then we will discuss applications of dielectrics and advanced application of dielectrics. So next we will talk about advanced materials, and we will relate it with the we will relate dielectric properties with the advanced materials. So advanced materials can be defined in different ways, and we already discussed about it, that broadest definition is to refer to all materials that represent advances over the traditional materials that have been used for hundreds or even thousands of years. So from this perspective, advanced materials, we can say that it refers to all new materials and modifications to the existing material to obtain superior performance in one or more characteristics that are critical for the application under consideration. So by modifying the previous existing material, we can make advanced materials that have outstanding properties, and we can modify according to our requirement. So advanced materials can exhibit or can show completely different properties. So these materials typically have properties that are superior to and that can outperform conventional materials in their applications. So development of advanced materials can lead to a design of completely new products. So advanced materials are could be modified, and that could be modified according to our requirements. So in case of advanced materials, we talk about nanomaterials or nanoparticles. So we already discussed about nanomaterials or nanoparticles in the introduction of nanomaterials. In other properties as well, we discussed in few points. So you know that nanomaterials are materials that have a size in the range of 1 to 100 nanometer, at least one dimension in the range of 1 to 100 nanometers, and below this range their properties are completely changed. When we talk about advanced materials, then the latest materials that are mostly being used as advanced materials are nanomaterials, and that are under considerations and that are mostly widely used and studied. Our nanomaterials are also known as nanoparticles. You already know about nanoparticles. What are nanomaterials? You have discussed, or you have studied this their introduction. So generally I will tell you in one or two lines that what are nanomaterials and nanoparticles. So nanomaterials or nanoparticles are that materials which have size in the range of 1 to 100 nanometer, and in nanotechnology we define a nanoparticle, a particle, as it is a small object that behaves as a whole unit with respect to its properties. So particles of any shape with dimension that is in the range of 10 raised to the power minus 9 to 10 raised to the power minus 7 meter are called nanoparticles or nanomaterials. materials. So, why dielectric nanomaterials are nanostructures or nanoparticles? So, why we consider them for dielectric properties? So, what kind of variations occur in the dielectric properties? If we consider that nanostructures instead of bulk materials are micron structures, that what kind of variations may occur in the dielectric properties of nanostructure materials? So why one needs to discuss dielectric nanomaterials, or why does one want to look at the applications of dielectric nanoparticles? Why they don't want to choose micro-sized or bulk materials? What is the importance of that nanomaterials? So the most important thing is that almost electronic devices, all electronic devices like computers or image processing devices, or you can say digital cameras, etc. Everything has integrated circuits or chips which have many dielectrics involved in it. So now these dielectrics in today's world are based on what is called MLCCs, that is the abbreviation for multi-layer ceramic capacitors, and the main material which is used as multi-layer ceramic capacitor is the barium titanate. So this barium titanate acts as a capacitor, and it is involved in the fabrication of chips, or it is applied in these devices. So this is utilized in these devices. So the size of chip, or the feature size as we say, is about 12 micron. It was 12 micron in 1990s. So below 12 micron, people could not make a chip in 1990s. But with the advancement of technology, with the advancement of the knowledge, and with the progress of working on advanced materials, today the size of chip has been reduced to nanometer range. In 1990s, it was about 12 micron size, but now the scientists can reduce the size up to nanometer range. So this decrease in size has the advantage that you can put many chips in the same area. So the total amount of number of chips that will be added onto the memory of that device, or whatever the property it is being applied for. So if you reduce the size of that chip, you can put many chips in one place at one place. So you can increase the memory of that device by reducing the size. So as you want to add number of chips on a particular in a package system in an electronic device, so if you reduce the feature size, if you reduce it up to nanometer range, then you will be able to put in more number of chips on a single device. So question is that how you can reduce the size of chip. This is very important. So as we are talking about multi-layer ceramic capacitor that is being used in these chips, so the thickness of these layers should be reduced. So multi-layer means that several layers of these ceramic capacitors are involved. If each layer is made up of barium titanate material, and if you use nanoparticles instead of micron size particles, then you will be able to put many such layers in one chip. So typical sizes below 100 nanometer will be required for such MLCCs or for multi-layer ceramic capacitor application. So the dielectric nanoparticles are very important because you can pack these nanoparticles in very dense manner, and they will still have a high surface area because the particle size is very small. If you can reduce this dielectric oxide nanoparticles to the size of nanometer, then you can think of making dielectric layers with less thickness, and that will be very advantageous by making the final size of chip very small. The other property which is of importance why we should go for nanoparticles of these dielectric materials is that these nanoparticles can be dispersed in a different matrix media. So you can have polymer, or you can have metals, composite. Many materials could be used as starting material, and that could be a matrix that could be dispersed with the dielectric nanoparticles, and they can be finely dispersed in a different media. So you can take a different starting material, and you can mix them with a different dielectric nanoparticles. So that is one important, and that is important, and you can make a composite like polymer dielectric composite, and then because of the polymer it will have a flexibility, and then you can make what are called flexible dielectric films or embedded dielectric films, where the dielectric nanoparticles are embedded within this polymer film. Like if you use a polymer with this dielectric nanoparticles, then you can prepare these flexible dielectric films, or these are also known as embedded dielectric films, because in this dielectric nanoparticles are embedded with these polymer films, and these are flexible. So such flexible films are of importance in flexible electronic uh, devices, especially in cell phones, in laptops, in another application, etc. So this is also very important for the other future applications. So now another importance of using nanoparticle is that in a dielectric measurements or dielectric materials, there is a strong dependence of the DC voltage for bulk materials. So you have to apply a high DC voltage, whereas if you reduce the size of nanoparticles, you can say that 50 volts applied voltage will lead to 60 to 80% loss in capacitance. So this dependence on the DC wires can be reduced, or it could be reduced by using nanoparticles. So less voltage could be used for nanoparticles. So another factor that is important is the lower loss of nanoparticles, which are dielectric nanoparticles. So lower loss means less dissipation factor. So a dielectric nanoparticles will have a much lower energy loss, or it has a less dissipation factor as compared to micron sized dielectric material or bulk sized dielectric material. So all these properties make it important for the person, for one, to understand and fabricate devices that are built up of dielectric nanoparticles rather than micron size particles or bulk materials. So if we reduce the size of these MLCCs material, then we can bring down the we can reduce the thickness of these layers. So hence these thin layers, dielectric layers, will allow you to make smaller devices. So if when we reduce the sizes, we can make smart devices. We can make smart devices that are smaller in size, but the ability or their properties are much better than the bigger one. So we can say that if we reduce the size of material, dielectric materials, we can prepare uh, smart devices, small size devices with enhanced properties. The other things is that we can prepare flexible materials if we embed them with a flexible polymers. And two other important points are that by using nanoparticles, you can overcome the strong dependence on DC voltage, and you can also lower the energy loss or dissipation factor by using nanoparticles or as compared to conventional or bulk particles. So there are different examples of dielectric materials for which many people are working. Examples are barium titanate, strontium titanate, lead titanate, and these are that have been prepared in micron or half of micron size, and people are further researchers are trying to reduce the size to nanometer range, and when size is shorter, when size is smaller, the one dimension is nanometer range, then the properties are further enhanced. So now if we look at the mixture of micro-sized and nano-sized particles, we can make a composites of nano and micron sized particles. As we discussed previously, that we can embed nanoparticles with a polymer matrix. So when we mix this micro-sized and nano-sized particles, you can see that when you are adding micron and nano-sized particles of the same material, for example, here we take the example of barium titanium oxide. You can take barium titanium oxide nanoparticles, the particles in micron sized, and also you can take the same material nano sized particles. Then you will mix these particles, and in this diagram you can see it shows that what these small particles will do. These small particles can join the large particles because the smaller particles has a lower melting point. It melts first, so it will help bonding these larger particles. So when you heat this smaller part melts first and it sinters. So you get in this scheme you can see that you will get this kind of grains of nano and micron sized particles which are highly compacted. So in this figure you can see, in this schematic diagram, you can see that these microstructures of nanoparticles and the micron sized particles, these are when have been sintered, then they combine together and they form a structure like this. These form micron sized uh, particles. So here is the figure for, you can see on the left side is uh, scanning electroscope micrograph for bulk barium titanate, and the right side is uh, scanning electron microscope image for nanomicron composite of barium titanate, where you mixed these bulk and nano material together. And here you can see the spaces which are due to the first melting of nanomaterials, and then they combine and they form a grain. And in this, only 1% of barium titanate has been added. And this kind of very compact grains, which shows signs of melting, it is due to the dielectric property. And this is only 1%, 1 weight% of nanobarium titanate that has been added to bulk material. So 99% is the micron size particles, and this 1 weight% is can vary the properties. So epsilon here is the dielectric constant, and when you plot it as a function of variation of the weight percent of nanoparticle, so you can add 1%, 2%, 5% like that is shown here for 30%. And you can see that for small region where addition of nanoparticle is around 1 or 2 or 3 weight percent, the dielectric constant epsilon as show an increase, and the dielectric loss, which is shown as a square, which is d, is the dielectric loss, is plotted on this scale, and that also show an increase in the d. So there some changes are occurring when you add nanoparticles to that dielectric micron particles. And this is mainly due to the addition of nanoparticles that changes the phase of that micron nanoparticles, and hence properties are changed. So ferroelectricity is a property of certain materials that have a spontaneous electric polarization, and it could be reversed by the application of external electric field. So all ferroelectrics are pyroelectrics with the additional property that their natural electric polarization is reversible. So if this polarization is reversible, then that materials are called ferroelectric, or that property is also known as pyroelectric, and the term is used in an analogy to ferromagnetism, and you already uh, uh, learn about ferromagnetism. So in ferromagnetism, what happened that in which material shows a permanent magnetic moment. Thus, the prefix ferro, meaning iron, was used to describe the property, despite the fact that most ferroelectric materials do not contain iron. But the property is in that case that they have a permanent magnetic moment, they have a permanent polarization, then we can say that that material is ferromagnetic, or that material is ferroelectric, depending on the iron. Ferro word is derived from the iron. So paraelectricity is the ability of many materials, which mainly include ceramics, to become polarized under an applied electric field. So this can happen even if there is no permanent electric dipole, as happens in ferroelectricity, that exists in the material, and the removal of field results in the polarization in that material returning to zero. So mechanism that cause paraelectric behavior are distortion of individual ions, displacement of electron cloud from the nucleus, and the polarization of molecules or combination of ions or defects. So this paraelectricity can happen or occurs in crystal phases where electric dipoles are mostly unaligned, and thus they have a potential to align in an external electric field, and they can weaken it. So example of paraelectric material of high electric dielectric constant is strontium titanate. So applications of dielectrics are mostly these are used in capacitors. So commercially manufactured capacitors generally use a solid dielectric material with high permittivity as the intervening medium between the stored positive and negative charges that are stored on the capacitor. So we can say this material as capacitor dielectric as well, that is used in capacitors. So another use of dielectric material, an example of dielectric material is barium strontium titanate thin film. From 2002 to 2004, the Army Research Laboratory conducted research on thin film technology. And barium strontium titanate, that is a ferroelectric thin film, was studied for the fabrication of radio frequency and microwave components. Such components may include a voltage controlled oscillators, some tunable filters, or phase shifters. So, this research was a part of an effort to provide the Army with highly tunable, microwave compatible materials for broadband electric field and tunable devices. So, which can be operated at constantly or consistently in extreme temperatures. So this work improved the modification of bulk barium strontium titanate, which is a thin film that enables the modification of electronic components. So in 2004, a research paper that was Army Research Laboratory research paper, they explored that how small concentration of acceptor dopants can dramatically modify the properties of ferroelectric materials such as barium, strontium, titanate. So when we modify or when we dope these materials, we can change the property of dielectric properties of that material. We can convert that para-electric material to ferro, or we can convert ferroelectric material to para-electric material as well. So, in this case, researchers doped barium strontium titanate thin films with magnesium, and they analyzed the structure, microstructure surface morphology, and film substrate compositional quality of the result. So, magnesium doped these barium strontium titanate films showed improved dielectric properties and low current leakage and good tunability for this material, which shows that there is potential for the use in microwave tunable devices. So dielectric materials can be solids, they can be liquids or gases. And in addition to this, we can say that high vacuum can also be useful, and it could be useful as a dielectric, even though its relative dielectric constant is only 1. So, solid dielectrics are generally the most commonly used dielectric that are used in electrical engineering. Many solids are very good insulators. So, some examples include for solids insulators or dielectrics are porcelain and glass, and most plastic can work as a dielectric. Air, nitrogen, and sulfur hexafluoride are three most commonly used gaseous dielectrics. So, in case of liquids, mineral oil is used inside electrical transformers as a fluid dielectric, and it is used to assist in cooling. So, dielectric fluids with higher dielectric constants, such as electrical grade castor oil, is often used in high voltage capacitors to increase the capacitance. So there are different examples of gases, solids, and liquids dielectrics that could be used in capacitors, and that could be used in transformers and other for other engineering purposes. Some ionic crystals and polymer dielectrics shows a spontaneous dipole moment, which can be reversed by applying an external electric field, and this behavior is called ferroelectric effect. We already discussed about it, that if we apply any electric field and this dipole moment is a spontaneous dipole moment that material could show, it could be reversed by applying magnetic electric field, and this is called ferroelectric effect. So these materials are analogous to ferromagnetic materials. They behave within an externally applied magnetic field. Ferromagnetic materials behave in response to externally applied magnetic field, but in case of ferroelectric, we apply external electric field. So ferroelectric materials often have very high dielectric constant, that can make them very useful for the use in for using in capacitors.